Stephen Self. I'm with Sustainable Interiors, and we're here today to do a energy audit on this house. I'm a certified ResNet HERS rater, and we're going to hook up a blower door and take some tests and see how energy efficient this house is. This is a fan for the blower door, and this will pressurize or depressurize the house to whatever level we're shooting for. Today it's 50 pascals, or about 20 miles an hour winds blowing on all four sides of the house. That's the test it best mimics. This is a duct blaster. It's a kind of a miniature version of this fan, and this duct blaster is hooked up to the HVAC equipment, the ductwork itself, and it'll test the leakiness of the duct system. And you will also be able to calculate the air changes required for the house and hand that information to the HVAC contractor, and they can dial in the HVAC and air requirements of the property. And that's basically it. Those are the two main components. The rest of it is all just information gathering and takeoff of what's here, windows and doors. Windows orientation is really the most critical bit of information we're gathering, but overhang and the amount of shading and how much energy those windows are letting out but also letting in is really what's being gathered. The amount of overhang that is covering the window, so your solar geometry, what level and intensity of sunlight is able to come into that window, and how much shading is protecting, especially on the western side of a building, how much shading is protecting it in the summertime. Have significant impact in the cooling and heating of a house, and how much it'll cost you to cool and heat the house. And since that's really what we're interested in gathering is the cost and the potential cost savings, the windows will play a key part in modeling the property. This would be an area of concern, of course. And this is actually growing into the house, but this is exposed here. And if this cantilever is connected to the building envelope inside, then this is a likely place for air and energy to moving in and out. And all it would take to seal this up is, you know, a piece of wood or a little bit of foam insulation or something, and this crack could really be controlled. It's often the dormers and the cantilevers that have the biggest discrepancy in pressure, and depending on who built the house and how well it was constructed, if those dormers or porches and things like that are sealed off properly, then they can provide a lot of cooling benefit and protection on the house. And if they're not, if they're open and exposed to the rest of the house, then you've got air moving back and forth, and there you go. Some tools that are used. This is a thermohygrometer. It tells the temperature and moisture, and I'll take an inside and an outside temperature as part of the audit. It's important because really what we're looking at is delta T, or the difference in temperature, when we're calculating efficiency and heat and cooling loss. This is a kilowatt meter. You can plug in any electric appliance and it will tell you exactly how much energy is being used by that appliance. And you can then determine if it would be cost effective to replace that piece of equipment. Another interesting thing I like to do with this is plug it in line with other equipment, cell phone chargers and any of those little charging devices, because what you'll find is that there are ghost loads or small amps that are being used even when those appliances are off. And in fact, big screen TVs, the plasma TVs, are notorious for that. They use quite a bit of energy even when they're off, so that when you turn them on, they'll come right back on. So this is a great device for isolating different electric usage in the house. And that's crucial, especially on a home energy audit, because the audit is a test that will be done prior to installing photovoltaics or any renewable energies. And so figuring out what your energy use is and then determining how to shrink that down prior to installing PV so that you only need need fewer panels is a crucial part of this as well. So that's this device. This is another temperature gauge, and this one can be installed into a duct system, and you can measure the temperature of the air coming out. The blower door. This is a blower door. Not a lot of people are familiar with this equipment. This is just a piece of fabric with a metal frame, and there's a fan in it, a little box fan. Currently, the fan is closed off. We'll take a baseline pressure reading, and then we'll open that up and see how much air is moving through the house. This is the fan controller and the DG700. This is a 2-channel pressure gauge, and we're monitoring 2 different channels, one outside and one inside. And that pressure difference is what we'll be capturing with the blower door. The DG700 pressure flow gauge needs to be told what blower door you're using, what ring you're using, and so each of those different options need to be selected manually every time. And as you're testing, you might change to a different ring, pull out the B ring and go to an A, and if you do that, that needs to be changed on the device, and that's a common place that folks get a little confused with a test. All right, so I'm going to go ahead and turn on the fan. Okay, what we'll find here is that we're not hitting the 50 pascals, and the DG700 is telling us that. Basically, it's telling us it cannot pressurize to 50, so we're going to take out another ring, switch the computer again, and fire it up again. I like to start out with the B because I find each of these are calibrated to a certain CFM. So the B ring will go from here to there, and okay, same thing happened, can't reach 50, and what we're seeing is that incrementally we're moving more and more air through the house with each of these rings. And we'll now go to, this is the B ring. We're going to take out the A ring, which will allow more air to move, and we'll be able to get a testing at 50. The 50 pascals, or 0.2 inches of water column, is the test, and that simulates a 20-mile-an-hour wind on the exterior of the house. And there's your score. So we're moving about 1,150 cubic feet of air per minute through this house. And that's pretty good. That's really good. And that's it for the test. Once you fire that up and you get your 50, your blower door is done, and you can move on to the next thing. It's pretty simple. It took a lot more time to set it up and make all those mistakes than it did to test. Basically, that number, CFM at 50, is 1150. 1,150 cubic feet of air per minute moving through here. And that number can then be used to whittle away at the leaks throughout the house. The cantilever, for example, on the eastern side of the house, we hypothesized that it could be a leaky spot. But with that low of an air movement number, 1150, which is your permanent baseline number, or is your current baseline number, you can make improvements and obviously get that number down. But we would assume that with the number being as low as it is, that the cantilever, for example, isn't a problem, or that the whole house fan might be the biggest significant source of air now by reason of deduction. Perhaps some of the access panels into the crawl spaces and attic would be other areas that we'd look at. And you can go through the house little by little and find those areas, improve them, come back and test, and we have an 1150 starting number. Let's say we make a small improvement somewhere and we get a 1100, and then we go and make another improvement and we come back and maybe we get that number down to 1,000 or 900. At a certain point of making improvements and retesting, you'll find that there's not a significant improvement, and when that happens, you know you're done. You can go take the door down and go on, and you've made this particular building as energy efficient as possible. This is a static pressure probe, and I'm going to put this in line into the duct system, and that will be the difference in pressure that we monitor with the duct blaster and the blower door. Now we have the duct blaster hooked up, and we're going to pressurize the house to 25 pascals. The previous test we depressurized to 50. That was the blower door test. The duct blaster test that we're about to do is total leakage to the outside of the building. And we'll bring the blower door up to about 25 pascals, and then we'll bring the duct blaster, pressurize the duct system to 0, and the difference in air amount is the total leakage to the outside of the building. Here we're going to assume it should be fairly low with our 1150 blower door number, but we'll test it. Ideally, we would be mounting the duct blaster to a furnace. The second best option is to find a return air, and that's what we've done here because of the confinement in the space down below. So ideally, you can mount the duct blaster directly to your supply, and it'll marry up perfectly. But obviously, field situations are different, and we're working with what we have here today. Okay, so we're at about 0 pressure and 175 CFM. Predominantly what we tested first was that the exterior of the building envelope, was fairly well sealed. Here we don't have a lot of ductwork in the attic or in uninsulated, unconditioned space. So our assumption is that most of the duct leakage is going to be to the inside of the house if there's any. And that's exactly what we found. If it were a little higher, we might want to look at sealing the ductwork, maybe with mastic, but that doesn't prove itself out here today. So we know we're done at this point, and we've done as much as we can in terms of both the testing and evaluating what systems might need to be improved upon, and we're at the point now where we know this is about as efficient as it's going to get. All right. It is, and there's a light. Oh, nice. All right. This is probably the most significant opportunity I've seen in this particular house. It's fiberglass, blown, and it's about 3 inches thick instead of 20 to 30 inches thick. So that would be a major place, a major improvement that can be made, and very low cost, just to blow in some cell over the top of this and increase the R to R50. The other thing that I'm seeing is that the whole house fan is really encased so that a lid could be put on top of it very easily. Now, it would require twice a year interacting, but that would be a significant place of sealing up that additional air loss, and easily done. All low-cost measures so far are the only thing we found that are really needed here. Nothing fancy, just some basic weatherizing, a little bit of insulation in the attic, which is more often than not exactly what you'll find. The attic needs a little insulation, and some basic weatherizing can significantly improve the structure. Temperature gauge that will show you variance in temperature here. You could also use a smoke stick that would show you the air movement. Here we have a basic lighter, and if we fire the lighter up, it won't even stay lit in the airspace. So that's a lot of air movement there, and we can demonstrate that at the whole house fan also. In terms of air movement, now it's not going to be as significant, but it is blowing out the lighter. So easy to find these areas. The best tool is your hand, and you can certainly feel the temperature change. Even on this light switch, the palm of my hand is very sensitive to that temperature air movement, and beyond that we can use the lighter, which is blowing out at this light switch. What we're not finding is that the windows are significantly leaky. What we're not finding is that all the doors and windows need to be replaced. That's not what we're finding. What we are finding are a lot of little air leaks that are moving air through the house, and that can be repaired very simply and in a low-cost manner. In terms of cantilever spots or exposure to the exterior, I can feel the air moving through this space as well. And I don't know if we can get a visual of this, but there's air pouring in through that cantilever area that we suspected, as you might suspect any cantilever area, to be kind of leaky because of the construction. Same as a porch or a dormer overhang. Those areas, if they're not completely isolated, bring a lot of air movement, and this is a great example of that right here. This is another common situation we find around a fireplace, is that there's a small hole somewhere, and although it's difficult to see, you're certainly not seeing it sitting around watching the fireplace. There's an enormous amount of air movement through here, and it's directly connected to the exterior. I can feel the air movement quite a bit, and this is a great place to seal up around the fireplace and make that improvement. This is also, we're feeling some leak here. This is the connecting wall, the party wall. which you would think would be the most airtight. Likely what we're experiencing is the chase coming down from the electrical penetration at the top plate is allowing that much air to come out here. It's not a lot. It is enough to disturb this lighter and practically blow it out. So it's a little surprising that in a wall that you would expect to be the most airtight has that much air movement through it. Can lights are a notorious air leak problem. I think if you've go into a house and you see a whole house fan, that's an obvious indication of some air movement. Also, can lights, regardless of IC, insulated can, the new IC lights, very leaky as well. I've felt both, the old style and the new style. There are some remediation techniques available if you can get access to the attic space above it, but these are notoriously leaky, even if they are the proper insulated can style. And this really disrupts the entire integrity of your building envelope by having penetrations throughout. Not to mention that these old incandescent bulbs are no longer even needed. What we would have here is probably LED lighting or some sort of direct lighting, but this is neither necessary from a technical perspective or is it beneficial from an energy efficient perspective. The plumbing penetrations coming through the wall, either underneath a sink in a kitchen like this or in a bathroom, are also great places to find a lot of that basic air movement. You can significantly reduce your air infiltration by sealing these up, and I'm feeling in here where the pipe comes through the wall, and I can feel the air moving through it around that plumbing penetration, very similarly to what we'd experience in electrical chase. Any type of an opening where that air can move through, no matter how small, it'll come through. Weird situation here. This is an access panel that's been covered with a register grill, and this is the access to the exterior of the building where the garden hose is attached. And what we're feeling here is a lot of air movement, and that's directly to the outside. So this exterior air is coming in and mixing with the HVAC system and getting pulled into the furnace and reducing the overall effectiveness and efficiency of that furnace. It spends a lot of time, effort, and energy heating or cooling that air, and when we introduce air that shouldn't be in that system, that's maybe too warm and moist, that causes problems. It can also lead to degradation of the heat exchanger inside the furnace. It's very common to find in utility rooms that it's either a sealed wall or that there's any insulation. Here you can see that this essentially leads directly into the floor joists and carries air all the way up into the kitchen, to the outlets, and to the plumbing protrusion underneath the sink. So all of that air is connected and cycling through the house in this way. And this is common to see this much exposure, and again, a great opportunity to seal this up and gain a lot more of that efficiency back that we saw at the blower door. Sink plumbing penetration, and you can feel a little bit of air coming through here as well. That's a significant issue when you're talking about indoor air quality, because as we know, a lot of cabinetry is made with compressed particle board that contains volatile organic compounds, VOCs. And what initiates those VOCs, even if the cabinetry is quite old, the two variables are heat and moisture. So we're introducing heat and moisture or some combination into an enclosed space underneath all this particle board. So that's why the plumbing penetrations underneath the sink are directly tied to IAQ, indoor air quality issues. I'm not feeling any air on this telephone jack at all, but what I am noticing is that there's a significant temperature difference. It's quite a bit cooler. And as we have that blower door fan running, that's really the benefit of having that running. Other than being able to just feel the air, it modifies the temperature in those air cavities that have air movement in them. and you'll feel that difference. You can also see the difference when, if you wanted to get into more and more analysis, we would do an infrared imaging of the temperature to see if the temperature here is different, and we could then focus in on that. And then you could get into thermal imaging if you want to get into some significant troubleshooting. It's certainly not required at this point because we can more than feel where we need to go in and make improvements. So a basic inspection of the utility room and the furnace, AC, domestic hot water is part of the HERS inspection. One of the things we'll look at that's very significant is the naturally aspirated combustible appliance, which is the need for the combustion air that we see coming in here, and that'll be a part of what we look at in terms of pressurizing the house and the potential for backdrafting. We don't see any of it here, which is a very good sign, but as we test the house and then contractors come in behind us and make improvements on the property, one of the things we don't want to have is that the house it's so tight it starts to backdraft from the furnace or the hot water heater. The serial number, I'll pull the gamma information off of this hot water heater as well as the furnace, check the efficiency, and put that into the software, into REM rate. And another thing we'll be doing is turning off of these units so that they don't fire up while we're doing the blower door test, and that's a crucial piece of the test. What I like to do is turn off a unit or put it onto a pilot, and then I put my car keys on top of there, so I can't leave unless I turn this back on, and then I know the hot water heater's back on, homeowner will be happy, so that's a good trick. So we've completed the HERS rating, the energy audit. We don't have a score yet because I'll need to go back and do the data entry into REM rate. But what we do know is that the house is a lot more efficient than we would have suspected when we first arrived. The blower door number is right around 1,000, 1,100. That's pretty good. We found some discrepancies in some cantilevered areas, and we found a lot of infiltration, exfiltration up in the attic area, and overall pretty good. The duct system is fairly tight, and we don't see a lot of leakage to the exterior of the building. So what little bit of duct leakage there is stays within the building envelope, and that's a good starting place as well. We found some room for improvement as well. A few holes that we didn't know about and the homeowner didn't know about. We also looked at the insulation level in the attic that could be significantly improved, and a fairly low-cost measure. In fact, all of the measures that we found that could be improved are all low-cost, low-tech, and easily done. It's a pretty good building overall in terms of the energy efficiency, and I think there's a significant opportunity to make those improvements low cost and relatively easily. My name's Stephen Michael Self, and I'm with Sustainable Interiors, and we just finished our HERS rating here today. Did I leave anything out? I don't know. It's a funny thing to talk into the computer.